Hi everyone, our research is a comparative analysis of salinity and conductivity in common flood zones of Ocean County. Coastal flooding is a recurring phenomenon that raises significant environmental concerns regarding water quality. Rising sea levels inundate low-lying wetlands and upland areas with excess water, and in return erode shorelines, further contributing to flooding events. Consequently, these surges of floodwater often transport saline water into groundwater aquifers. This process, known as vertical saltwater intrusion, increases salinity levels in freshwater systems and disrupts natural balances. Salinity and conductivity are fundamental indicators of water quality in coastal environments. Salinity reflects the concentration of dissolved salts in the water, while conductivity measures the water's ability to conduct electricity, which increases with higher ion concentrations. Elevated salinity and conductivity can have immediate physiological effects on freshwater organisms, which often have narrow tolerance ranges. Rapid changes in these parameters can impair osmoregulation, reduce reproductive success, and lead to declines in sensitive species populations, ultimately leading to biodiversity loss and altered ecosystem function. Furthermore, persistent high conductivity signals prolonged exposure to salts and other dissolved ions, which can accelerate soil degradation and reduce the viability of salt-sensitive crops, thereby affecting local agriculture and food security. Heavy rainfall and storm-driven runoff also interact with floodwaters, altering pH and transporting nutrients and contaminants that exacerbate water quality issues. The combined influence of salinization, elevated conductivity, altered pH, and nutrient-rich runoff increases vulnerability of both natural habitats and human activities along the coast. Ocean County, New Jersey represents a region particularly vulnerable to such challenges. Barrier Island communities, including Long Beach Island, Ship Bottom, and Seaside Heights, are highly exposed to recurrent flooding and storm surges. Historical events such as Hurricane Erin and have demonstrated the magnitude of these risks by reshaping shorelines and disrupting freshwater resources. Studying salinity and conductivity in these flood-prone areas provides critical insights into the spatial variability of vulnerability and provides insights on strategies to mitigate salinization impacts on ecosystems and agriculture.
The water samples were collected from 9 frequently flooded sites located in Ocean County, New Jersey. At each site, the water samples were collected from floodwater in the street and stored in labeled WorldPack sampling bags or jars. Sampling occurred during the fall and winter seasons from October 12th to January 10th, when coastal flooding events were the most common. In Seaside Park, we sampled at M Street, L Street, and F Street. The sampling sites at Point Pleasant were Trenton Ave, Foreman Ave, and Atlantic Ave. And our last sites were in Long Beach Island on Taylor Ave, 28th Street, and 85th Street. Salinity and conductivity were then measured for each location in the lab. Salinity was measured using a refractometer in parts per thousand, while conductivity was measured in microsiemens using the YSI unit. After all the measurements were recorded, the water data was organized and analyzed in RStudio. Scatter plots, linear regressions, and time series plots were created to examine the relationships between conductivity, salinity, and rainfall, using the R-squared values to assess trends. ANOVA tests were ran using R to compare conductivity and salinity between the locations. Using data collected from 2021 to 2022, another ANOVA test was performed to find any significant differences between the salinity and conductivity values over time.
We sampled floodwater across 3 distinct locations over 4 months. On average, Seaside Park showed a conductivity of 20,969 microsiemens and a salinity of 11.1 parts per thousand. Point Pleasant averaged 20,834 microsiemens and 11.5 parts per thousand, while Long Beach Island followed closely with an average of 19,648 microsiemens and 10.5 parts per thousand. And here's our weather data that we collected. You can see that when we collected our peak salinity values on October 12, 2025, with values ranging from 26 parts per thousand to 31 parts per thousand, that was during a period of heavy rainfall with an average of 1.73 inches. Additionally, December 12 was the day with the lowest average rainfall of 0.88 inches, and the samples we collected all had a salinity of 0 parts per thousand. Here's the first graph we created using R and RStudio. It's a graph of the relationship between the conductivity and salinity values we collected, and with the R-square valued of 0.927, there is a strong positive correlation between salinity and conductivity. As salinity increases, the concentration of dissolved salts rises, enabling charged particles to conduct electrical current and
Thereby increasing water conductivity.
Our second graph shows the relationship between total rainfall and conductivity. The R-squared value that was calculated is 0.526, meaning there's a moderate positive correlation between water conductivity and total rainfall. This pattern indicates that higher rainfall leads to increased water conductivity due to storm runoff carrying dissolved ions. Our final graph illustrates rainfall over time at each location, showing that later rainfall resulted in less severe flooding at the sites. Additionally, for this project, we compared our data to the data collected in LBI from a past MATE student. The historic data has an average salinity of 15.9 parts per thousand and an average conductivity of 24,507 microsiemens. To see if these changes were tied into specific towns or shifted over the years, we ran a series of ANOVA tests. The first series of one-way ANOVA tests were to test for differences in salinity and conductivity between Seaside Park, Point Pleasant, and LBI. The results were not significant for both salinity, with a p-value of 0.982, and conductivity, with a p-value of 0.987. The second series of tests used a two-way ANOVA which compared our data collected to historical data. The results further indicated that salinity did not differ significantly by location, with a p-value of 0.691, or by time period with a p-value of 0.162. Conductivity also followed the same pattern with a p-value of 0.969 for location and a p-value of 0.544 for period.
As expected, salinity and conductivity showed a positive correlation because the higher level concentration of dissolved ions increases the water's ability to conduct electricity. Additionally, conductivity and the amount of total rainfall showed a positive correlation in the study, indicating that there are more dissolved salts in the water where there is more rainfall. This is likely due to the prolonged runoff that heavy rainfall creates. As the surface runoff flows, it carries the minerals, salts, and other ions into the floodwater. Another reason is due to saltwater intrusion. The heavier rainfall raises the water level and allows the saline water from Barnegat Bay to mix with the flooded water in the streets, bringing the saltwater inland. In our study, rainfall and conductivity exhibited a positive correlation. However, this relationship likely reflects storm-driven processes such as surface flooding, saltwater transport, and increased mixing, rather than rainfall directly increasing salinity. October 12th and October 30th had a higher amount of total rainfall due to the nor'eastern that moved along the east coast, bringing heavy rainfall, coastal flooding, and strong winds. Additionally, the nor'eastern causes high wave energy to hit New Jersey's coast and led to high salinity levels from saline water being pushed onshore. During December and January, weaker storms impacted the New Jersey coast, contributing to the lighter or lack of rainfall during these months and causing many of the testing sites to not have severe flooding. In November, there were no strong storms that provided any accumulation of water at the testing sites. Although all sites on January 10th received over 1 inch of total rain, there was minimal wind to push the bay water inland. This allows the rainwater to fall directly on the streets and accumulate without mixing with any salt water. Additionally, because rainwater is fresh, the higher volume of water may have diluted any salt spray or minerals that the water may have collected, reducing the salinity overall.
The insignificant results from the one-way and two-way ANOVA tests between Long Beach Island, Seaside Heights, and Point Pleasant, as well as past data, indicate stability across these sites for salinity and conductivity over the years 2021 to 2026, with a p-value greater than 0.05. Based on the little variation between these parameters, an inference can be made that all sites are impacted by their distribution and movement with influence from incoming storms. Our study establishes a guideline for salinity and conductivity for further studies to use as a comparison when assessing future environmental changes that relate to pollution, development, or climate effects. However, these parameters that are seemingly stable may change over time due to the unpredictability of future climates. That's why continuous monitoring is important. In the event that these salinity levels become elevated in the future, an unusually high salt content in waters where species aren't adapted for saline can cause duress and cause long-term effects on its surrounding environment. To conclude, our findings show that salinity and conductivity are positively related. Moreover, heavy rainfall and storms push coastal waters more inland and even more severely in high tide conditions. And because of this, salt water is more likely to mix with floodwater, causing higher salinities. This explains why October 12th, when the nor'easter occurred, had the highest ratings in both conductivity and salinity in comparison to the rest of our other testing dates. And because these sites are closely connected to surrounding soils and groundwater, if heavier storms were to occur, greater water pressure from these storms could be directed into porous soils and groundwater aquifers, contaminating fresh water and making it unfit for drinking and other use. In early October, the 3 sites averaged more than 20,000 microsiemens. That showcases significant saltwater presence. Overall, the positive correlation between rainfall and conductivity demonstrates that flooding events are the main contributor to saltwater intrusion that reflect the extent of seawater penetration. In retrospect, there were many aspects of our project that we could have improved. One of the things we would do differently is record the bay salinity so that we would have a reference point to see the severity of saltwater intrusion for our floodwater. And for the same reasons, collecting tide and floodwater heights would also have been beneficial. Additionally, in the 2025 to 2026 season, there were very few floods, resulting in fewer numbers of samples than preferred. If our project was executed over a longer period of time, with more instances of actual floods, our project would have more variability and reliability. We'd also like to acknowledge Mr. Werner for letting us use his equipment and for helping us along the way, as well as Amelie Werner for letting us use her data from 2021 to 2022 on LBI.